Hello. Continuing with the case of magnetic effects of current, we will be starting off with the Ampere circuital law. Now, according to this law, it states that if there is a current carrying conductor and there is a bit of magnetic field associated with the region surrounding it, then if we are to take an imaginary loop, or rather a loop, whether it's imaginary or not, it's immaterial. But if we consider a loop around it, and let's say that's having a certain radius or circular loop, it can be any kind of loop, any shape, but nevertheless, a symmetrical one would be essential. So, if we are to consider the line integral of the magnetic field that is associated with that current carrying conductor, and take the line integral of the magnetic field over a closed loop, that loop which we have considered, that is equal to mu naught, which is the absolute permeability of free space, because we are considering the observation in the free space. So mu naught times the total amount of current that is enclosed by the loop. In this case, the total amount of current that is enclosed is I. Now, I would like you to draw an analogy to the case of Gauss theorem, if you remember, in electrostatics, which had a similar sort of condition. Only thing, there are few the parameters were different. In that case, there we had a static charge, or some amount of charge, let's say Q, which was supposedly enclosed within a closed surface, and within that surface, if we were to consider the linkage of magnetic lines of force with the surface or the walls of that surface, then the net amount of flux that is associated, that is equal to E dot product with the surface area over that entire closed surface. The integration is taken over the entire surface, and that is equal to 1 over epsilon naught times of the total charge enclosed. Now there you had the static charge which was enclosed by a surface. Here you have the moving charge which constitutes the current flowing across the conductor, that multiplied to, well, not 1 over mu naught, but mu naught times the current that is enclosed. And also the case that you can draw a difference over here is that obviously you have the magnetic field instead of the electric field, but also here you are taking the line integral of the magnetic field. Now if you were to apply the Gauss theorem in magnetostatics, obviously that's going to result in a zero, because the magnet always is in the form of a dipole. So as a result of that, even the smallest portion of a magnet taken inside a closed surface would result in the net flux becoming zero. But that's another topic to discuss about. However, this is what we have as the Ampere circuital law. And just like the case of the Gauss theorem, which helps us to determine the electric field intensity, this one over different places, or different charge distributions, here as well, for different variations in the type of conductors that we are considering, uh, we can easily obtain the magnetic field intensity without any it's completely hassle free. So let's just look at an example of a previous attempt that we did to obtain the magnetic field using Biot-Savart's law, which was pretty hectic, although the derivation has been uh, stripped off. The syllabus has been stripped off the derivation. The derivation has been struck out in case of a straight conductor. But we have already seen that how the derivation would have been pretty tedious in the first video itself in this playlist. But using the Ampere circuital law, which is in short taken as ACL, we can obtain the magnetic field that is associated with a straight current carrying conductor. Now, the only thing that would limit us in this case is that we won't be obtaining the term for a finite length of a conductor. We will have to consider the infinite length. Now, for the infinite length of the conductor considered, we may choose a point which is at a perpendicular distance, let us say A, from the given conducting wire, and there we wish to determine the magnetic field intensity. Now, in order to do that, we will be applying the Ampere circuital law, where we will be constructing an imaginary loop. There it was the Gaussian surface which we were imagining. Here it will be the Amperian loop, and most of the times it's symmetrical. So what we are discussing here is the first application of the Ampere circuital law, which involves the detection or the value obtaining the expression for the magnetic field at a perpendicular distance from a straight conductor carrying current. We have already obtained this in Biot-Savart's law, but the derivation, as you know, was not a part of the syllabus. However, I have shown it. But over here, we'll be considering a complete derivation, which is in fact a part of the syllabus, so we cannot really ignore it. So this is the first application where we have to determine the magnetic field at a perpendicular distance from a straight conductor carrying current. Now, obviously, it has to carry current, because without the current flowing in the conductor, you won't be having a magnetic field associated with it in the first place. So we apply the Biot-Savart's law over I beg your pardon, the Ampere circuital law. So over the closed loop that we have taken, the radius of which is in this case A, because A is the perpendicular distance of the point where we have to obtain the magnetic field, that is at the point P, uh, from the straight conductor which is carrying current. And B dot dl is equal to mu naught times the current that is enclosed in this case is simply I. Now remember, if we have supposedly a current which is flowing in some opposite direction, in that case, then we would simply consider the let's say this is I dash, then the net current in this case is either I dash minus I or I minus I dash. Well, that symbol over there depends on which direction we are considering. So it's either I dash minus I or I minus I dash. Uh, but that is a separate discussion that we'll be obviously trying out in the problem section. So this is B dot dl times of mu naught I, so that is equal to mu naught times of I. So that gives me B, and one thing that you must keep in mind is that we are considering over here the direction of dl along the direction of the magnetic field. We have chosen that direction because as you can see, if you use the right hand palm rule at the point P, the magnetic field will be going into the plane at that point. And also the elementary length that we may consider across that loop, dl, that is taken tangentially and into the plane. So if this is the loop that we have considered, this is the point P where we wish to obtain the magnetic field. So we will be taking that into the plane, that is dl, the elementary length that we have considered, that is taken into the plane and along the direction of the magnetic field. So this will result in B dl cosine of 0, because they are along the same direction. Cosine of 0 gives me 1, and dl is now therefore integrated, because this closed loop is a circular loop, so we have to integrate it from 0 to through to the circumference of the circle, which is 2 pi a in this case, a being the radius, mu naught times of I, and B therefore is equal to, well, that would result in a 2 pi a on the left hand side with the integration done and dusted, and then finally mu naught I on to the right hand side. Finally you have the magnetic field to be equal to mu naught times over 2 pi a, which is again the case that we had obtained in case of a straight conductor of infinite length. And we need not be concerned about the direction, because we have already chosen the direction of the length along the direction of the electric field. So the direction is not a big thing to worry about in this case. The only thing that we need to obtain is the magnetic field intensity associated with that current carrying conductor. So this is more or less the first application which we have for the Ampere circuital law, and we'll extend the application further into obtaining the magnetic field for a solenoid, which is the second application. Now, solenoid, as you know, is simply a wire wound over a given, let's say, a core. And if the core isn't available, then this is an air cored solenoid. Now, as you can see the direction of the current, to show you a detailed view of it, we'll just slice it through its cross section, and then we, not literally slicing it, but at least we can imagine this cross sectional slice of it, which would give us, let's say there was a core over there, and the core had the windings on it. So at one end of the core, what I'll find is the current is coming out from that point and getting into this point. Then it is coming out from this point once again and getting into this point. So that would give you a complete setup of the solenoid with, let us say, n number of turns. So this is n number of turns over length L. So you have n, which is the number of turns over unit length, which gives me n over L. That would be necessary in order to determine the magnetic field. Now, with all of that, now as you can see that the current carrying wire is coming out of it and getting into it along this direction. So it will be as if it will be coming out from that point going in. Then if I were to consider the flow of current and the direction of the magnetic field, I know from that of Biot-Savart's law that this is going to be, the magnetic field is going to be along that direction. So this solenoid now behaves as a completely bar magnet, where the magnetic lines of force are actually moving along that direction. Now, what we wish to know is that we want to obtain the magnetic field within the solenoid at any given point, except for the end points as of now. So let's say we were to determine the magnetic field over that point that I have drawn, that I've just made. And in order to do so, what we construct is an Amperian loop, this time a squared Amperian loop, with each side of the square having a length, let's say, small l. We name the loop as A, B, C, and D, and we apply the ACL over it, over that closed loop through A, B, C, D back to A. And we now consider mu naught times of, for an air cooled solenoid, of course, we consider mu naught times of the current. Now we do not know how many current carrying wires are within that given squared loop, although you can see just one and a half, and like that, but that's not, there will be plenty of windings within that, because they contain about 2000 turns per unit length, or many more as far as possible. So it's very difficult to determine. So what we do is, for a single loop you will be getting one value of the magnetic field, and for n number of turns you will be getting uh, n times the magnetic field, as we have learned earlier. So how many turns are exactly there within that small length L that you see? Now, if there are capital N number of turns over the capital L length, then there are n number of turns per unit length. Then over length L, you will have n times of L uh, as the number of turns, and each turn would contribute to the magnetic field. So that will be that many times the current, or with each turn associated. So then you have B dot dl taken over the loop. I'll be considering segments of it from A through to B, then B through to C. Then I'm not repeating that B dot dl everywhere. That's understood, it's there. And then from C to D, and then from D back to A. We'll forget about the right hand side as of now. We'll focus on the left hand side. Now, what happens over here is that the segments AD and BC, as you can see, AD and BC, they will go to 0 simply. Why? Because the length of those loops, the length will be perpendicular to that of the flow of magnetic field which is horizontal over here. So dot product of that is going to be 0 because cosine 90 will end up in 0. I hope you are clear with the vectors in that case. And then in that AB segment, what happens is that the magnetic lines of force, they do not move along that AB. They will form a loop, and this is a sufficiently small loop, small Amperian loop that I've considered. So those lines of force or the magnetic field lines, they won't come within that region which carries AB. So here the magnetic field itself is absent, so that goes to 0 as well. So only you have the field associated with the segment CD. And if we integrate that, and as you can see, DL with that length available is along the magnetic field. So B dl cosine of 0 goes to 1, integrated from 0 to L because that length is L, and over here you have mu naught times N times of L times of I, and so this is BL and mu naught N L I. The L's get cancelled on both the sides, so you need not be concerned about the length of the loop that you have taken. That's going to go away, and you also need not be concerned about the number of turns per unit, number of turns in total. You will be getting the result in terms of number of turns per unit length. So this is the expression for the magnetic field associated with a solenoid. Now, as far as the end points of the solenoid are concerned, the end points will carry a magnetic field to be equal to, this is an extra point that I would bring to your notice just for knowledge sake, that this is going to be mu naught N times of I over 2. You can remember it. A hack that I will provide you is that the loop that you will be taking, Amperian loop, those will have to be symmetrical, and there at the end points you will get a half a symmetry, and so as a result of that, probably half the magnetic field. We are not going into the details of it. This is just a method that I mentioned you so that you can remember that at endpoints the magnetic field is halved. So that's more or less from this video on Ampere circuital law and two of its applications. This is what the course has for us, although we can discuss about toroid in some separate video, but that is for later. We'll be trying out few numericals about on this topic. That is for the later videos that I'll be making. Till then, thank you for watching.